Right, so carrying on from this content, where we had transistor-based switching circuits that were fed with an input sensor that was light, dark, hot, cold, or positional, or maybe even a switch, providing an output, whether it's rotation or light or whatever, and you had to describe the operation of these transistor circuits. What I'm going to do is add in another component that makes it, again, a little bit more realistic. And after we've finished this bit, I'm going to introduce you to a component called a relay. After we've introduced the relay, that's pretty much as complex as these transistor circuits will get, okay? So again, you have to recognise a relay, be able to name the relay, be able to draw a relay, and be able to explain the operation of a transistor-based circuit that has a relay in it, and be able to understand the operation of it. Okay, so let's explain why we would need a relay in the first instance, what a relay is for. So if we're going to yank and have a look at a circuit, right? What I've got here is a circuit that detects high temperatures. So this could be in like a hospital where you're detecting the temperature of a patient. So if the person's temperature gets too high, an audio alarm sounds, right? And again, it's got a sensitivity control in there that people would have to engage with. You know, you could consider that if the temperature sensor's on someone's forehead or on their abdomen or inside their ear, you know, there's different physical locations where you can take a temperature, and in those different physical locations, different temperatures constitute a high temperature, okay? So that's why you would have to be able to change the sensitivity of this thing. So you can imagine a nurse perhaps changing the setting on this in order to calibrate the alarm depending on the patient, perhaps physical characteristics of the patient, or on where the temperature sensor is placed. So again, this could be a little plastic potentiometer that someone turns, or in industrial settings sometimes it's a screw and people put a wee screwdriver in and turn the screwdriver. So you could imagine that perhaps a wee 12-volt buzzer, it's not going to be that loud. It's not going to be loud enough that if this was on a patient in a ward that had 10 beds in it, with a charge nurse sitting at a desk outside, they're not going to hear that. They might not hear that 12-volt buzzer going off. We really want that buzzer to be high energy, so it's really, really loud. How could we do that? Well, that seems quite obvious. Just increase the voltage here. Just make this a massive... Let's plug it into the mains. A 230-volt buzzer. Nobody's going to not hear that. The problem with that, and I hope you can see this, is that this is a temperature sensor that's attached to a patient in a hospital. You don't really want to attach a mains temperature sensor to a patient in a hospital. Also, people are going to have to interact with the sensitivity setting on it. You don't want people putting screwdrivers against components that are wired up to the mains. That's really, really dangerous. So we find ourselves in a situation where we really want the input side of the circuit to be low energy, like battery level, 12 volts or whatever, 9 volts, a square battery. Whereas we want the output side of the circuit to be really, really high energy. How do we do that? That's where a relay comes in. So a relay is a component. Here's the relay here. There's the symbol for a relay. And you can see that half of the symbol is just a switch. And you actually get different relays with different switches in them. And relays are... Oh wait. Relays are named... Oh, I don't have the other relay in there. Relays are named for the kind of switch that they've got. So that's a single pole double throw relay. And you can get single pole, single throw, and so on and so forth. You know all the different switches by this point, hopefully. Okay, so a relay is an electromagnetic device. That's basically a solenoid in there. When you pass current through it, the solenoid will either outstroke or instroke, depending on how it's set up, and change the state of that switch. Really handy. Notice the 3 connections in that switch are not connected to the relay coil. They are electrically isolated from the relay coil. Okay. What we'll do is we'll take a wee screen grab of the relay and we'll take a wee note on that, right? In here. So relays. So named for the switch. You could be copying this down. Switch is isolated from coil. What does that mean? It's not connected to it. it's insulated from it. There'll be no current flow between either side. Yeah. There's like 0.1, 0.2. Another point would be it's used to separate high energy outputs from low energy inputs. That's its function. Okay. Let's just annotate it a wee bit just so that you know. That is a coil, or it could be a solenoid. Let's just move that text over there. Coil or solenoid. This side is the switch. This guy up here gets called the common. You can see that this relay is in the off position and the common is connected to this one. And these have names. And this guy is called the normally connected. And the other one, so in its resting state, this one is not connected. So it's called the normally open. Okay, and we might use abbreviations NO, NC, and COM. So you do have to be careful when you're using a single pole double throw relay. You have to be careful what you connect to. Okay, we'll discuss that back in Yank in a wee second. These are your two coil connections. So you just treat the coil, you just treat that as an output device in a transistor circuit. So that's what a relay is, and that's what it's used for. When you pass current through the coil, the switch will change state. Let's just put that in there. So that's like a third point, and here's our last point. When you pass current through the coil, the relay energizes and the switch changes state. These things are mechanical, so they actually make a sound. You hear relays clicking, and originally it was relays that controlled the lights in your car, so that's why your indicators would click on and off. It was the relay switching on and off, and that's what would make the clicking sound. The idea would be that the current that's passing through the bulbs in the front of your car to make your headlights really bright is a really high current. You wouldn't really want to route that current up the steering column in front of the driver in case there was an accident, or even, you want to keep your cable runs as short as possible, because long cable runs with high currents equals a lot of heat. So you keep the high current cable runs really short and just have low current cable runs up to the switching on the steering column. So that's why we'd have relays. Obviously nowadays there's other devices and other lower current bulbs, which means you can run cabling all over the place, and these things are controlled using microcontrollers and stuff. But they kept the click, so that's why your indicators still make a noise, and the noise is basically modelled on the noise that relays actually make. So a relay is an electrically controlled switch, which is also what we're using the transistor for, but the difference is we can use one current to control a much larger current on the output. That's supposed to be fair, but we can do that with transistors as well, but we don't do that with transistors at National 5. Right, okay, so that's what a relay is. How do we use it in this circuit? Well, what we do is we take the buzzer out and we put the buzzer as a component on its own, and we're essentially going to make a completely separate circuit over this side. We're going to use this switch, the buzzer, and a separate power supply, and a really large power supply. Probably going to have to check the properties on this relay before I do it. Max current contact voltage, so let's change that to like 250 I don't know if I can make that any bigger. I might end up destroying the relay here, but we'll see what happens. Right, okay, so I'm going to connect that to that and that to that. Now, if I connect the buzzer to the normally connected, then it will be on straight away, so I don't want to do that. I want to connect it to the normally open. And then I can connect the relay as my output device in my transistor circuit. Ooh, so what I've got now is a low voltage input side at 12 volts and a really high energy output side. This might not work, it might fail. Obviously it will fail because I don't have a diode in, but a relay is an electromagnetic device, so I have to protect the transistor from back EMF in the relay coil. There you go. Well, hopefully that will work. I'm going to just check this out before I do it. Will work to a charm. Right, so there you go. So I've got a low energy input side and a high energy output side, and they're separated by the relay coil. I'm going to take a wee note on that guy as well now. That come in here. Again, this is the kind of thing that you might want to copy out. So we've got a high energy circuit on this side. Low energy circuit here. Low energy input circuit. And then on this side we've got a high energy output circuit. And they are separated by the relay in the middle. Notice these two circuits are not connected to each other. They're not electrically connected. So if you ever build a circuit in Yenka with a relay, the common mistake is that people join that rail to that rail. Yeah, that's why I try to draw them offset like this, so that you know two completely separate circuits. And output is connected to the normally open. So there's a couple of things that you could change about this. This is one of the questions that's came up in mistakes and stuff. So this buzzer will come on when it's hot. Okay, if that was the wrong way round, what could you change? If the buzzer was supposed to come on when it was cold, you could swap these two round and make this a cold sensor instead, or you could swap that connection round, and that would mean it would come on when it was cold. Yeah, so that's where we're at. That is the end of the content. What I want you to do is to explain the operation of this circuit, where you mention every single component by name and tell me what it's for, and make sure you get the point that this is a let's go, a temperature sensor for critical care patients. That's why it has to have a really, really loud output. Okay, so your task is to explain the operation. Now this is as long as it will get. So the only addition to the other stuff is when you start talking about the relay, and you start talking about why there's a relay there to separate these two types of circuits. But make sure you still talk about when that buzzer comes on at high temperature and so on. You also want to talk about what you know about the connections. Basically, you're trying to show off your level of knowledge in these questions. Okay? Give that your best shot. Thank you.